Hello, class, and welcome to part 5 of Rocks and Minerals. In this section, we'll be going over metamorphic rocks. So a metamorphic rock is formed directly from any type of rock under extreme heat and pressure. So this could be a metamorphic rock going under heat and pressure, sedimentary rock going through heat and pressure, or an igneous rock going through heat and or pressure. And again, this is on page 7 of your Earth Science reference tables, the scheme for metamorphic rock identification. So at the bottom of page 7, this is the chart that you will see. All of the metamorphic rocks are on the right-hand side in bold. Okay, slate, phyllite, schist, gneiss, anthracite coal, hornfels, quartzite, marble, and metaconglomerate. And just like the sedimentary rock chart, there's map symbols that denote which is the rock. So all information about each rock is also found in the same row as that rock. So it reads the same way as a sedimentary rock chart does. So what are the changes that occur in the rock due to metamorphism? We see a recrystallization of unmelted material. There's an increase in density because of it being pressurized. Okay, there's being pushed into a smaller space. There will be a distortion of the rock, okay, from the pressure, okay, or the heat. Okay, it's going to change the way it looks. So when we talk about foliation, okay, foliation is the visible alignment of minerals and crystals. In the bottom picture, okay, there is no foliation. Okay, the mineral arrangement is before, okay, it's scattered throughout. But once stress or pressure is applied to either side, the minerals will realign and create basically alternating colors of bands. Okay, and that's called banding. The light colored and dark colored bands of minerals that form parallel to the foliation. So here's some further examples from what we just saw. So the non-foliated texture is on the left-hand side, and on the right-hand side is foliated texture. In the pictures, we see that there's no direct alignment with the crystals. So this is just be an example of contact metamorphism. Now, contact is just heat being added. The regional metamorphism on the bottom right-hand side is where pressure is being applied. So there's two different types of metamorphism. There's contact metamorphism and regional metamorphism. So up top here, these are all examples of regional metamorphism. Slate, phyllite, schist, and gneiss. Now you see on the texture on the left-hand side, it says foliated. Okay, and then it's got subcategories of mineral alignment and banding. Banding is where we really see the alternating colors. Okay, we don't see it so much within the schist, phyllite, or slate. Okay, but banding is where you'll see a majority of the alternating colors of black and white. Now, the non-foliated rocks, which are at the bottom of our chart, okay, there's no visible alignment of mineral crystals. So examples would be quartzite and marble. Okay, and they're located on the bottom of our chart. And you'll see that the types of metamorphism for down the bottom. Okay, anthracite coal is regional, hornfels is contact, and then quartzite, marble, and metaconglomerate could either be regional or contact metamorphism. So the key feature when we look at a metamorphic rock is the banding of alternating colors. Okay, being able to see the distortion and the mineral alignment of the crystals. So here's some examples of those. Now, regional metamorphism occurs when large areas of rocks are under intense heat and pressure associated with mountain building. Okay, this brings us into plate tectonics, okay, where we see the plates shifting, and as they collide into other ranges, okay, it'll cause a lot of pressure amongst these rocks, and it'll cause folding and everything else. And if it was really deep below the earth, okay, it may come in contact with the asthenosphere, like warmer temperatures from the asthenosphere, which would change the temperature. So all of our foliated, okay, rocks are regional metamorphism, okay, with anthracite coal, and also the three on the bottom, quartzite, marble, and metaconglomerate. So contact metamorphism occurs when molten rock comes in contact with the surrounding rocks in a small area. So this might be an intrusion of where magma is making its way through the earth, and it's coming in contact with the rocks around it. So it's not melting the rocks, but it's going to change the temperature of the rock that it comes in contact with. Now, the term parent rock, it means the rock that the metamorphic rock formed from. So this is important for us to recognize as we go through the chart. So when we look at the comment section, we'll find a lot of the parents there. So the parent rock for slate is shale. Okay. The parent rock for anthracite coal is bituminous coal, both of which are sedimentary rocks. When we have hornfels, it's formed from various rocks changed by heat from nearby magma or lava. Quartzite comes from quartz sandstone. Marble comes from limestone or dolostone that's been heat and pressured. And the metaconglomerate is just the metamorphism of conglomerate rocks. Now, actually, let me go back to this chart. When we look at slate at the top, okay, it's a low-grade metamorphism of shale. If slate is more pressure and temperature is applied to slate, it'll turn to phyllite. If more heat and pressure is applied to phyllite, it'll turn to schist. If more heat and pressure is applied to schist, it'll turn to gneiss. Now, gneiss is the end of the road. Okay, this is high-grade metamorphism. If any more heat or pressure is applied to gneiss, at this point it will turn into an igneous rock. Okay, it would melt and become a liquid, okay, and solidify as an igneous rock. So here's an example of contact metamorphism. Molten rock, which is an igneous intrusion, causes limestone in zone A to metamorphose into what? Now, if you remember from our chart, limestone will turn into marble. So our checkpoint. The diagram below represents a sample of a rock. Now, as we go through these checkpoints, make sure you pause the video, try to answer them on your own. Why would this be classified as a metamorphic rock? Okay, it's because the rock has banding. Remember, banding is that alternating colors of light and dark minerals that have been forced by the pressure that's been applied to it. Now, a student is on a field trip in New York State collected a sample of metamorphic bedrock containing bands of coarse-grained crystals of plagioclase feldspar, pyroxene, quartz, and mica. Identify the metamorphic rock found by the student. Now, if you look back at your chart, okay, it's important to identify that there are layers, okay, also that it's coarse-grained crystals. So if we go back to our chart, we'll see that that is gneiss. It also contains the minerals of plagioclase, feldspar, pyroxene, quartz, and mica. The cross-section below shows a portion of Earth's crust. Layers A, B, C, and D represent rock units that have not been overturned. Name the metamorphic rock formed when sedimentary rock layers A and B undergo contact metamorphism because of igneous intrusion C. So this is the same diagram we saw in the sedimentary rock video. When the igneous intrusion at C comes up through the Earth's layers, okay, it's going to come in contact with A. A is limestone. So if limestone goes through metamorphism, through contact, it will turn into marble. For layer B, if B goes through contact metamorphism, when it comes in contact with this igneous intrusion, okay, and B is sandstone, B would turn into quartzite. The photograph below shows a large outcrop of rock composed primarily of visible crystals of mica, quartz, and feldspar. Based on the composition and the foliated texture, which metamorphic rock can this best be identified as? Now, the key words within the question was the foliated texture. So we know it's got to be a rock on the top of our chart. Now, it also tells us that it has visible crystals of mica, quartz, and feldspar. So this will be classified as schist. Base your answers to questions 5 through 7 on the cross-section below, which represents the bedrock structure of a portion of the lithosphere. Layers A through D represent locations in the lithosphere. Identify one of the most abundant minerals in metamorphic rock at location A. So as we look at this diagram, okay, we see a subducting plate of oceanic crust. So this must be at a plate boundary of where the continental crust is coming in contact with the oceanic crust. We have a granite mountain core caused by the melting of older rocks. So at one time, this must have been an igneous intrusion that was coming through. Where we see C. C is high-grade metamorphism of gneiss. Then as we get farther away from gneiss, you can see the metamorphism grade decrease until it gets to slate. Now what it asks you is about A. A is going to be calcite because this is identified through the metamorphism of marble. So all of A is marble and is asking what the most abundant mineral in marble is, and it's calcite. Now that could also be said that if it is calcite, we can identify it by using the hydrochloric acid test, just like we would for limestone. Okay, remember limestone has a brick pattern. If we look to the left-hand side, right above where B is, okay, we see the brick pattern that was limestone. Okay, and as it got pressurized, or as it went through metamorphism, we see on the right-hand side that brick pattern turned into a pretty rough-looking brick pattern. Okay, that would have calcite in it. 6. Identify the grain size of the metamorphic rock at location D. Now we see D at the bottom. D is identified as the rock hornfels. So if you look at your reference tables, you can see the grain size of what hornfels is. And that is fine. 7. Explain why the type of rock changes between location B and C. So as we see B, we see the shale. Then it goes to slate, to firelite, to schist, to gneiss. Why would there be a change of rocks between locations B and C? Okay, because heat and pressure is applied from B to C because of regional metamorphism. The most intense metamorphism, okay, will be the highest grade, which is gneiss. And as we get farther away from the amount of pressure, the grade of metamorphism lowers, okay, all the way down to slate. And then slate was the metamorphism of shale, which we see in B. Now that ends majority of our notes and video on rocks. And this is a little bit of a cheat sheet, okay, for you guys to know the classification of the rocks and what are the characteristics. So you have an igneous rock if you look at the left-hand side of the screen, it has interlocking crystals. It has a piece of pegmatite. Okay. If it has a glassy texture, or if it has vesicular gas pockets. You have a sedimentary rock. Okay. If it has fossils, it has particles or fragments of rock joined together, or if it has horizontal layers and shades of the same color. Okay. And then our final lesson, we talked about metamorphic rocks, and we can identify if it's a metamorphic rock if it has banding. Okay, which are stripes of different colors that may be bent. Thank you for listening. Hope you had a great day.